It's all good.
Yes, oh, perfect. Thank you very much. Thank you, Sasha, for invitation. As Sasha said, my name is Weronika Gorczyk, and I work at the Center of Exploration and Targeting at the University of Western Australia. And today I would like to take an opportunity and tell you a little bit about a reworking of the Archean cratons that we have here in Western Australia. But because you are mostly on different continents, I put you in the context where we are. So Australia is mostly built of the three major cratonic bodies, which is the Northern Australia Creighton, the Southern Australia Creighton, and the Western Australia Creighton, plus the things that have accreted sometimes later on to the east. And today I will tell you a little bit about the margins of the Western Australia Creighton, which itself is made out of two cratonic body, which is Pilbara Creighton and the Yilgarn Creighton, which have accreted together at the end of Archean region. And saying that, I will concentrate on two margins. One is the east-northern margin of the Pilbara Creighton, which is called Rudall Province, and the eastern-southern margin of the Yilgarn Creighton, which is Albany, Fraser origin. And at first, we're going to move towards the Rudall Province. So, zooming in into the area where we look at here at the map of the depth of the crystalline basement, what we can see here is we have the Pilbara Creighton, and on its edge we have the Rudall Province, which is the margin of the Pilbara Creighton, and on the going further north, we have a thing that we call Kitson Creighton. That is then to the north, we have Kimberley Creighton, which is part of the Northern Australia Creighton. So with that, what is interesting here, so until less than a year ago, we were considering that potentially the thing that we call here Kitson Creighton is part of the extended Pilbara Creighton. But recent passive seismic line that has been shot from the Pilbara Creighton through the Rudall Province, Kitson Creighton to the Kimberley Creighton showed us that underneath the Rudall Province, we have a certain seismic structure which looks like a crocodile mouth. And this has been interpreted by the authors of the paper that is now in review as an amalgamation of a microcontinent to the Pilbara Creighton at around 1900 million years ago, and that that would leave that particular margin of the Pilbara looking in the same way. So the lithospheric mantle would have looked similar since the time of 1.938. And it has been verified by the hafnium isotope work, which showed that the samples from the gabbros that intruded in at around 830 million years ago have different hafnium signatures. So from the Pilbara side of the Rudall, that is different from the signatures that come from the Kitson side of the margins. And the Rudall Province and everything that happens here happens within this wedge between the two major lithospheric structures, which is the Vines Fault and the parallel range fault. So then when we're going to look later on what happens in the Paleoproterozoic, the area experiences multiple intrusions of mafic and igneous volcanisms, and they are all associated to be related to the extensional settings. So through the whole time of the Paleoproterozoic, we have multiple magmatic events which are concentrating only within that particular region, the Rudal province. We see not much of, we observe magmatic events within on the other side of the Kimberley Creighton, within the Capricorn orogen, but there is nothing else that is observed here lower down, or we haven't sampled it yet, which is also a big possibility. So with saying that, when we move, so the whole Paleoproterozoic, the whole area is an extension. Then when we move to Neoproterozoic, and this is the time when the whole Central Australia has been submerged in the water and has been called the Centralian Super Basin, which started at around 900, around 1009, let's say 1 GA. It's the beginning of the super sequence 1, to which and during that time, everywhere within the Centralian super basin, we have a very shallow sedimentation. But the Rudal province, which is now called the Yanina Basin, exhibits depositional in a much deeper environment than the rest of this large extensive sub-basin. And the main reason for that is that the area is potentially in some sort of an extension, and that coincides with the timing of the intrusion of the Dew Gabbro, that at around 8:30, which is potentially part of the larger scheme when of the Rodinia breakup, when Laurentia departed from Australia, and you had the rifting along the Adelaide Rift, which failed. And at that time, we had a large igneous province which intruded through the Southern Australia Creighton and then went to the west north, propagated to the west north, and potentially that was the one of the failed branches of the rift that allowed for the extensive deepening of that particular basin at that time. But what is very interesting in that sense is that despite of this extensive reworking and multiple events that happen at that margin, we don't really see much of the movement with and a lot of displacement in terms of extension in that particular region. So despite of a visual extension in the rocks and in the whole behavior and extensive magmatism, it all stayed in place, and we still see the structure that was potentially left from the amalgamation of the microcontinent at around 1.9 GA. But then when we're going to move to the other side of the Western Australia Creighton, and we look at the Albany Fraser orogen, so what we see here is that the structure of the Albany Fraser orogen is perpendicular to the main structure of the Ilgan Creighton, and that might be significant in some sort. And with that, as the previous Creighton, that as the previous margin, this one also exhibits extensive extensional settings for during the Paleoproterozoic, and the way it has been interpreted by the Spaggiari and co-authors is that the barren bay at first during the Paleoproterozoic we had extensional settings in an intraplate as an intraplate rift basin with multiple magmatic events with increasing amount of melting with time, and later around 1600 a breakup, an opening of that particular rift, an opening of the ocean in the area, and occurrence of the arid basin, and then we have Albany Fraser to be interpreted as a passive margin. So if we look at the cartoons of that particular set of events, what we see is that for around 200 million years, so from 1800s to 1600s, we have an intraplate extensional setting where we have rifting taking place through all of this time, and multiple events of magmatism, but the rift doesn't actually break at that particular moment, and it's only at around 1600 where we end up with rifting, let's say detachment of the part of the continental crust and an opening of the oceanic crust. So with that, what we see, we have two different working environments for the two cratonic margins, and then just because I like numerical models here, you're gonna have an examples of how numerically we can see the difference between extension of the passive margin of the cratonic margin with the mantle temperatures, which are here representative of today's world, and here are the temperatures of the mantle are actually 200 degrees hotter than today, and what we observe is much greater in that case, and also in the case where you have a pre-existing structure at the edge of the margin, is that you see extensive stretching of the mantle and the hyperextension within the crust that takes place over an extended period of time, and potentially that would allow of the buildup of the wider margin before it drifts. So with that, I will conclude or not. Okay, and with that, I'm going to conclude that despite the fact that the two margins, they experience very similar tectonic, they're exposed to similar tectonic forces, they tell a totally different story, and the reworking of those particular margins is different at the time. And then if we can call it the Rudal province as the margin of the Kimberley Creighton, it is still to be told, as there are many questions to come. And I think with that, I'm going to say thank you very much. And as you can see, looking at the rocks in both places, it's very splendid. There's a lot of outcrops and it's a lot of joy. Thank you very much.
Thanks, Weronika. I wanted to interrupt you at 10 minutes, but you did not make any pause. But we have ample of time left for questions now. You were very much in time. So if there are any questions, please put them in the chat. There's no question so far. Suzanne, did you have a question?
Sure, I can ask a question. Thank you, Weronika. I mean, I love this old rifts and the challenge that is involved to actually find out what happened so long ago. I mean, it's tremendous, not?
Well, especially from the amount of samples that we have available, it's really storytelling.
Absolutely. But I would like to ask a question about your numerical model. So
yes,
the model that you showed at the end. So in the top two models, the extension localizes still within the continent.
yes.
I understand where it localizes in the bottom right because you put the weeks on there, but why does it localize where it does in the top two models?
I think that's a very good question. It's a work that I haven't published, so I haven't thought about it a lot because I've done it for the project of the Albany Fraser for a while, and then I turned out actually having little ones, so I abandoned that at that time. But it is a good question, and at this point I don't really have the answer. It might be and my PowerPoint time.
Yeah, we can see your inbox now. That might not be what you want to show either.
Exactly. Let me close that if I can. Oh, I think oh, there we go. So no, but so saying that, I think it's it is the extent of the continental crust that potentially might allow for that localization in that point.
Yeah, it would be interesting to look at that a bit further, I think, because in your warmer model, it still seems to localize in fairly the same place. It's quite fascinating.
Yes.
Yeah.
Okay. Well, but it might be a good reason to actually go back to those models.
Mm-hmm. Yeah. Thanks a lot.
Thanks.
There's one raised hand by Rune. Would you like to ask a question?
Yeah, thank you very much. I mean, thank you, Weronika, for a lovely presentation. You modeled that the mantle was 200 degrees centigrade warmer back when you did your modeling. What is this estimate based on? I mean, is this because you have a mantle plume, or is it just an assumption that the mantle was generally warmer back then?
So it is generally it is put on the fact that at that time the mantle was generally warmer at that time, and there is a lot of I know that there is a lot of controversy on that particular aspect, and then people so there is a variety of papers that talk about the potential temperature of the mantle going from the Archean time, having the range of 300 degrees difference to around 100. So there's a wide range to choose from. So I'm very open-minded, and in that particular set of runs that I've done, I've tested them at every 20 degrees, and I think around 100 degrees you got a shift in between the two regimes, and I just randomly chosen one at this particular point.
Okay, so basically you would get pretty much the same results whether you choose, say, 100 or 300 degrees centigrades.
Well, no, I think the higher temperature you get, the more partial melting you end up having.
Yeah. Makes sense,
right?
doesn't it?
That increases the dynamics of the mantle or not. So that's and unfortunately the code that I am using doesn't really deal very well with quenching, and so it's extremely dynamic with that. So looking at the high amount of the higher amount of partial melts pre-existing in the initial setting makes it a bit more dynamic that you would expect.
Okay, thanks a lot.
Mm-hmm.